Okay, so I'd like to welcome you all to the event of the day. This is a debate, formal debate on the subject, is Mars 1 feasible? We have two teams here to debate this proposition in formal style, negative team and affirmative team. In this case, the negative team is going to go first. Okay, the negative team consists of Sidney Doe and Owens. These are doctoral students from MIT in aerospace engineering. They published a very strong critique of the Mars 1 plan a number of months ago and received international press coverage for it. To answer this critique or any other criticisms they may have, we have Boss Lansdorp, who is the president of Mars 1, and Barry Finger, who is an engineer with the Paragon space company, which designs life support systems for NASA and also did the life support system design for both Inspiration Mars and Mars 1. The rules are going to be this. The negative team is going to go first. They are going to speak for 20 minutes, sharp cutoff. Okay. Then the affirmative team is going to speak for 20 minutes, sharp cutoff. Then 10-minute rebuttal from the negative, 10-minute rebuttal from the affirmative, and then we're going to open it up to questions, which can be directed by you to either party for a 1-minute response, and then the other side will get to respond to that with a 1-minute counter. So this is the real thing. This is, for instance, a much better debate than you might have seen on TV last week. No gloves. Okay, and that's important. No, let me tell you something. This is a very controversial proposition, and we're going to debate it. And I must say that both sides here are to be congratulated for having the integrity and courage and come out and defend their point of view in clear and open debate face to face. Okay, because we've had too much in the space business of people going around saying stuff behind other people's backs and not coming out in the open to say it openly and confront it, or other people saying things openly to the press but not being willing to come and defend their point of view. We, of course, had the instance of Franklin Chang Diaz saying very detrimental things, that radiation's a showstopper on the way to Mars, so we must go to Mars much quicker than is currently possible, and only the Vasimir drive can enable this, and thus you can't go to Mars until the warp Vasimir is developed. You can't do your program until we do his program. And he's been challenged to come and defend these statements repeatedly and not done it, which should tell you something, that not only are his statements not defensible, but he doesn't consider them defensible. In this case, one of these two parties is wrong. Okay. Okay, but they're honest. And they're willing to come out and say, look, it's not just a question of the Vasimir. We've had all kinds of things being put through the space program on irrational, indefensible grounds, like, for instance, the shuttle program, the space station program, and now the asteroid redirect program. Okay? We've lost decades because the space program has been run in an irrational way. Okay? The way to get to reason is through clear and open debate. And so we're going to make this a practice at the Mars Society conventions from now on. We're going to have major debates about major issues. We're having this one tonight. Tomorrow night, it's where next for human exploration? The moon. Harrison Schmitt is going to represent that tomorrow night. Mars, I am going to represent that position. And then Mars orbit, which is a proposal that has been put forth by the Planetary Society, and Casey Dreyer is going to represent that as well. So that's going to be a three-way debate. But anyway, let's get started. Negative team, begin your remarks.
this if Okay. Well, first off, I just want, hopefully the technologies cooperate. It's really an honor to be here. It's great. We're so glad to have this opportunity to be here. As you said, to be part of an open discussion. Let's talk facts, let's talk evidence, let's talk about what needs to be done, what we need to do to get to Mars. And so I'm Andrew Owens. This is my colleague Sydney Doe. We are PhD candidates at MIT. We want to give a little background. As you mentioned, we wrote a study last year. We wanted to acknowledge our co-authors on that study. There's Sam Schreiner and Koki Ho, who have both graduated. Sam's now at JPL. Koki is an assistant professor at UIUC. And also our lighting system fades in and out, but Professor Olivier Deweck, who's our thesis advisor out there. So we are really excited about spaceflight in our lab. We look at mission studies, we look at strategic engineering, technology development, looking at what does it take to get us from here to Mars, wherever we're going next, what does it take? So one key point that we wanted to make is this is not a debate about the feasibility of exploring Mars or colonizing Mars. I think everyone in this room can agree that humanity will settle Mars, right? Is there anyone here that doesn't think that we should go to Mars? No hands. Good, I guess based on the name of the convention. This is a debate, as you described before, about a very specific question. Is the Mars One mission plan feasible? And by examining this question, which may be yes, maybe no, then we can learn what we need to do to make Mars exploration feasible. What technologies do we need to develop? What are the major challenges that we face? So that's what we're here to discuss today. So to start off, what is the Mars One plan? I think we're all pretty familiar with it, but to cover the main points, looking to build a colony with one-way trips, 4 crew members every 2 years, using existing, validated, and available technology, and then $6 billion for the first crew, $4 billion for the rest. First mission launches in 5 years, 2020. And the first crew landing in 2027, so that's 12 years. This is what it says on the Mars One website. And here, just laid out in a schedule, we have the first mission during a ComSat in 2020. Then we've got a rover and a ComSat 2 years after that. The first cargo mission, 2024, 2 years after that. 2 years after that, the first crew goes. And then from then on out, it's crew, another crew, staying on Mars for the rest of their lives because it is a one-way trip that does not have a return system. So this is the Mars One plan. This is what the Mars One website says. This is the scope. So what does this mean? It means that Mars One claims that system design, development, test, manufacture, integration, and 14 launches will be accomplished for $6 billion over the next 12 years to accomplish the first mission landing. And then every 2 years after that, Mars One will manufacture, integrate, and launch 11 systems for $4 billion continuously to sustain the crews that are on the surface. This is the Mars One plan. This is how it is described on Mars One's website. So now we're going to talk a little bit about feasibility.
So the topic of this debate is Mars One feasible? So the question is, how do you assess feasibility? So every project is constrained by 3 important factors, and these are interrelated with each other. These are cost, schedule, and scope. So this is sometimes called the triple constraint of projects, or the iron triangle. And these are interrelated, they're synergistic, and you have to look at a project holistically from these 3 factors to assess feasibility. If any of these change, then the other factors have to change accordingly. So feasibility, one way, or actually the way of assessing project feasibility is to answer the question, is the defined scope attainable within the schedule and cost constraints that have been stated? So let's apply this model to the Mars One project. As Andrew had mentioned, the scope is to permanently settle the planet Mars via a series of one-way missions with 4 crew every 2 years. They want to do the first landing on the surface of Mars by 2027, so that's 12 years from now. And the claim is that this can be done for $6 billion, then afterwards $4 billion every 2 years. So the key question that frames this entire debate tonight is, can Mars One execute the Mars One mission plan that's laid out in front of you under the cost and schedule constraints that they have specified? And so over the next 15 or so minutes, we'll be digging deeper into what it means for the cost, schedule, and scope of Mars One. How are these claims made in the context of our historical knowledge, the facts that we've seen from our aerospace experience and analytical studies. And we've also color-coded some of the words in this presentation, so this green, red, blue theme will go on throughout. And so we want you to keep in mind that when you're looking at a project, you have to look at it from these three main factors: cost, schedule, scope. So Mars One has made several arguments for the feasibility of their plan. Some of them include the argument that it is feasible from a schedule perspective, and this is usually made through comparisons to Apollo. So a quote is, don't forget that when Kennedy announced the moon mission, he had less time than Mars One. Other arguments have been related to the scope of the mission. And the key argument is that because it's a one-way mission, it allows for existing technology to be employed. So here's a very long quote that Mr. Lansdorp has made. I'm not going to go through it all, but essentially the takeaway is that the technology is existing to do a one-way mission, that we have landing systems that are very comparable to that of the NASA Curiosity mission, and that life support systems are very similar to those used on the International Space Station. So let's look at each of these claims of feasibility in a little bit more detail. So let's look at the Apollo comparison argument, for example. So as we all know, Neil Armstrong stepped on the moon in July 1969, and this was 8 years after the start of the Apollo program. And to get Neil Armstrong to the moon, NASA had to develop many technologies. Here we've outlined the major technology developments, and we'll see them here. So these are the main technologies. And to land humans on the moon, in current year's dollars, this costs $102 billion. I guess we can't see the bottom there. Now let's compare this to Mars One. I'll continue on, given we're on a time crunch here. So let's look at the Mars One mission. They've started in 2011, and they have 12 years left to meet their goal of landing a crew of 4 on the surface of Mars. So based on their website, this is the hardware that's required to land 4 people on Mars. So there's a lot more technologies that are required. There are a lot more instances of each technology, and each of these entails a dedicated program. And the claim is that this is $6 billion. So you're probably all thinking to yourself, this is not really a fair comparison. NASA's a government agency. Mars One is a private mission. It's a lot more efficient. So let's compare Mars One's cost, schedule, scope to a more modern-day private mission. Let's compare it to Virgin Galactic. So as many of you know, Virgin Galactic is planning to develop a regular suborbital spaceflight capability. They've been at this for 10 to 11 years now, and as of November 2014, after 10 years and $600 million invested, they're still under development. If you look at the Mars One plan, they still have 12 years remaining to send humans on one-way missions to Mars, which is a lot harder than sending people 100 kilometers above us. So another argument is that technology is existing. So let's look in detail at one of the many technologies that are required. So a key cornerstone of the Mars One plan is that they'll use an intelligent rover. And essentially what this rover does is set up the habitat autonomously. And so what they're asking of this rover is for crew transport, a truck and trailer, a bulldozer, and a very autonomous, dexterous, intelligent robot. All of that in one single system, operating on the surface of Mars for at least 26 months, and without any servicing from any of the crew. Basically, no capability to repair the system. So right now, we can't even do this on Earth. And this is expected to happen on Mars. So if we compare this with something that's, with another rover that's on the same schedule relatively, we can look at the Mars 2020 rover recently announced by NASA. So this is based on existing technology. It's based on the Curiosity bus. It's a scientific rover, so it doesn't have to do any any heavy lifting, sorry. It has coring drill. It has some technology demonstrations. And the cost of this is $1.2 billion, with $130 million of which being science instruments. So the estimate for this rover is 1/5 of the entire budget of Mars One, and it's for a much less capable vehicle. Another argument has been landing systems. They're very comparable to the NASA Curiosity mission. So let's look at all the landing capability that we've had. The best that we've been able to do after 40 years of sending robots to Mars, is to land 899 kilograms on the surface. On numerous occasions, Mars 1 has stated that they will land 2,500 kilograms on the surface. That's payload, so that's 2.8 times what we've been able to do. And if you account for the mass of the lander itself, so the vehicle that's carrying that equipment, that brings this multiplier up to 7.5. Now, put another way, if we stack all of these bars and compare it with the total mass that we've been able to land on the surface of Mars, the requirement for Mars 1 is almost double that of everything we've been able to land on Mars in the past. And I'd like to note, finally, that the bar on the far right here is a mass estimate for a life support system that Mars 1 recently announced. And so that's even heavier than what's been previously budgeted by Mars 1.
So the next technology that we'd like to look at is life support systems, and these have often been compared to life support systems operating on the International Space Station right now. So the question is, what happens on the International Space Station? This is our long-duration spaceflight experience. We operate this station right in low Earth orbit. It's very close by. You can actually see it go over in the right conditions. And what is really interesting here is the ISS goes about 3 months between resupply missions. So the endurance of the system is 3 months. If something goes wrong, you come home. If something goes wrong, you send a spare up. You're okay. With Mars 1, you have a 26-month interval between resupply missions. That's an 8.7 time increase in the time that this system needs to operate without input from Earth. And there is no abort option. So one of the big things that we've learned from the International Space Station, from operating life support systems, is that these hardware require servicing and repair. You can see these pictures over on the side. Astronauts spend a lot of their time performing maintenance on the station. And this is a station that was designed to be maintained with the ORUs to actually sacrifice mass to minimize crew time. So they're spending all this time now just to keep it going in low Earth orbit with all of the spares that we can throw at it from the ground. And this spares question is an important one to look at because the demand for spare parts is a very significant mass driver. It's a very significant part of logistics. So this chart here, for example, shows as a function of the probability that you want to have that you have brought enough spares, what massive spares you have to supply for a life support and ISRU system for a 26-month operation on the surface of Mars. And this blue line is based upon ISS demonstrated reliability from the systems that we've operated. So you can see here that even to get a coin toss opportunity that the system that is keeping you alive, you will have enough spare parts to maintain it, you have to launch 3 Dragons worth of spares, land 3 Dragons worth of spares on the surface of Mars. And this is just for one crew for one 26-month interval. So one thing you might say is, well, of course, but we would increase the reliability of those systems. So let's double the reliability. Sorry, I forgot one point. That's the Mars 1 allocation for supplies in their mission plan as posted online. 1 Dragon for supplies. So, but if we double the reliability, you have very much the same problem. Even to get a coin toss, it takes 3 Dragons. If you want to get up into the high 90%, 4. Spares are a very, very significant problem. And this reliability increase doesn't come free. Cost increases exponentially with reliabilities of the system. You also have to account for the testing time required to assure those reliabilities. There are lots of challenges with increasing the reliability of a system. So that was just for one crew. What happens if we look at the crew buildup in the Mars 1 plan? What this means is as more and more crews are operating on the surface, more and more life support systems are operating on the surface, they require more and more spares. And this shows the spares profile over time of life support and ISRU systems. So the first crew must bring enough spares to sustain themselves for 26 months. The second crew needs to bring enough spares for themselves and the first crew. The third crew is bringing for 3, the fourth crew is bringing for 4, and so on. And the mass of spares grows over time. So a growth in spares mass means you need more landers. It means you need more launches. It means that the cost grows over time. So the resupply cost of a series of one-way trips to Mars grows unsustainably over time. And this is true until you have the capability to fully manufacture spare parts using only local resources on Mars. And so it's important to note 3D printing was mentioned in the earlier panel. That's actually part of my dissertation topic. I'm looking at how to apply 3D printing. Yeah, it's an interesting idea, right? How to apply 3D printing, how to address these logistical challenges. But it's a major challenge because even if you put a 3D printer there and you're sending feedstock from Earth, you need more and more feedstock over time. So this was really the fundamental conclusion of the paper that we wrote a year ago. The Mars 1 strategy of one-way missions is inherently unsustainable without a Mars-based manufacturing capacity. So this was the big conclusion that we presented at IAC a year ago. this is one of the major challenges that faces human spaceflight and the idea of a sustained settlement on another planet. And this is the reason that we do these kind of reports, to identify these challenges and lay them out. If we want to settle sustainably on Mars, we have to generate a manufacturing capability. So Mars One recently released their own report, which was the Paragon study, and I think it's important to compare what our report a year ago and the Paragon report a couple months ago looked at. So if we look here, there's a set of functions that were examined by both reports. Some were examined by Paragon, and we didn't have them in our report. Some were examined in our report and weren't considered in the Paragon study. For the 6 systems, 6 primary processors that were included in the system, 5 out of the 6, Paragon and us, selected the same technology to accomplish the function. The difference was in waste processing, where we used a urine processor, you used the membrane drying technique. And it's interesting to see that if you look at the mass estimates that came out of both of these reports, they're pretty close. They're in the same ballpark, so it's not all that different. And the bottom line here is the primary conclusion of our IAC study was that the cost grows unsustainably over time. And so the Paragon conceptual design study does not examine the feasibility of the Mars One mission plan. It presents an ECLSS design concept. It examines the requirements that an ECLSS would have to meet. But it does not address the cost. It does not address the development schedule within what Mars One has laid out. And it's limited in scope. In particular, it does not address the life cycle properties that were enumerated in our report, which we believe are the major challenge to this plan. And it's important to note that they come to several of the same conclusions that we did. For example, the plant systems were removed from the life support system, and also mentioned the need for a manufacturing capability on Mars.
So we've just spent the last 15 minutes talking about the cost, schedule, scope. And we've been trying to gain further insight into this fundamental question: can Mars One execute the Mars One mission plan under the cost and schedule constraints that they have specified? So let's summarize what we've seen so far. In order for Mars One to accomplish the project plan that they have laid ahead of us, they have to develop all these elements. And it's not just all of these elements, there's a time component to it as well. In the next 5 years, they need to develop a lander and a COMSAT. 2 years after that, they need another COMSAT and another rover. 2 years after that, they need to send their first cargo missions to Mars, so that's 6 more full capsules. And 2 years after that, they're going to send their crew. And then after that, every 2 years, they're sending all those systems there for Mars. And that's claimed to be done for $4 billion. Now, in addition to that massive scope and this unprecedented launch cadence, there are several development challenges that we've highlighted. So they need to develop at least 7 major systems. These include an intelligent rover, which is far more capable than what we have on Earth, let alone Mars. They need to improve the landing capability by at least 7.5 times. They need to improve life support endurance by at least 8.7 times. And they need to address what we think is the most important problem: the fact that the cost of the program grows unsustainably over time. And this is, again, to reiterate what Andrew said, it's because your spare parts requirements grow as your crew grows. And there's additional challenges that we haven't highlighted here. So these are all very large and massive challenges, but are they impossible to solve? No. Very big challenges, and they require a lot of resources, a lot of time, and these are the challenges that myself and other researchers, both at MIT, across the US, and around the world, think about every day, because our belief is that if you're really going to send humans to Mars, you need to do studies, identify the challenges, and go through the research, development, and technology development and maturation process to help enable this. But that's not really related to the question tonight. The question tonight is, can Mars One accomplish the project plan that they have stated? And that is, can they accomplish these development challenges for $6 billion in the next 12 years? Our belief, based on the data, the analysis that we've made, and the historical analysis that we've done, is that no, they cannot do this, and it is infeasible. However, our goal tonight was the facts and the evidence for you, the audience, to make this decision for yourself. Thank you.
Good evening. Please, can I see hands? Who here is 45 years old or younger? So like all the people that just raised their hands, I was not alive. Younger I asked. Like all the people that just raised their hands, I was not alive when all of humanity held its breath and witnessed the most exciting history of our planet, the landing of the Apollo 11 mission. I was born 8 years later, in 1977, but I have lived the Apollo mission through the recordings that all of us have seen so many times. Had Neil Armstrong walking down the ladder, carefully placing his foot on the lunar soil, his brilliant quote, "A small step for a man, one giant leap for mankind." Neil Armstrong and Buzz Aldrin hopping along on the lunar surface in the low gravity. Yeah, that's amazing stuff. And to me, the moon landing is still the pinnacle of perseverance, ambition, resilience. It's all that and more. It's one of the few moments in history where the whole world came to a standstill for a positive reason. It's now 46 years later, and still these recordings inspire millions around the world, including me. So a few facts about the Apollo missions. When Kennedy presented his plans in '61, that was 4 years after the first human went to space. Sorry, the first satellite went to space, the Sputnik. It was 1 month after the first human went to space. No American had been in orbit around the Earth yet when Kennedy said we will land a man on the moon before the end of the decade and bring him back safely. More than 50% of the attempts to reach orbit by the US failed, the unmanned launches. More than 50% failed, and Kennedy said before the end of the decade, etc. In 8 years' time, all that was developed and much more. And we needed rockets to go to the moon. We needed the portable life support systems, the moon landing systems, computers. All that was developed and more in just 8 years' time. So why am I talking about the moon? We're going to Mars, right? Well, there's a number of similarities between the Apollo program and Mars 1. Both were and are clear and audacious goals. Both need a lot of work to be implemented. And both are in the pre-phase A stage of development. Mars 1's goal is not to send humans to Mars in 2027 with a $6 billion budget and 14 launches. Our goal is to send humans to Mars, period. For that reason, I actually consider the study that Andrew and Sydney did a confirmation of Mars 1's plan. Yes, this is feasible. Our plan is not etched in stone, and we've already announced 2 delays. We were originally landing in 2023. Maybe some of you remember that. Reality catches up with your plan, and that's okay. When Sydney and Andrew released their plan, Mars 1 did not embrace it, which I think we should have. I think that was a mistake by Mars 1. We should have embraced the plan because it shows that permanent Mars settlement is possible. And Sydney and Andrew did this demonstration with a completely different approach than Mars 1, and with existing simulation models for deep space missions. Look at this picture. It's the only other slide I have. Top left, you see the expected design in May '61. To the right, June '61. To the right, July '61. To the right, December '61. Our plan is at the same stage as Kennedy's plan was when he announced it in the pre-phase A phase. Our plan will change. It will look nothing like what you see in the pictures. So there's many similarities between the moon mission that Kennedy proposed and our mission, but there's also many differences. The most important one, when Kennedy launched his plan, almost none of the technology was existing. For us, a lot of the technology does exist. Not the actual systems, but the ways to build these systems, the actual physical principles, the materials, they do exist. They don't need to be invented. Completely different than the Apollo mission. Another important difference was that Kennedy had the unlimited resources of NASA. Well, we do not. Mars has actually quite limited resources, and that has been the only reason that we've had to announce our 2 delays so far. If I had to choose between organizing a mission to Mars without having any of the technology or without having any of the money, I would choose to organize this mission without having the money, because I think it's a lot easier to raise money for a mission like this than to develop the technology. So we've recently received a report by Paragon Space Development Corporation for our life support system. This is exactly what Mars One is about right now. We need to finance all the studies by all our different aerospace suppliers, established aerospace suppliers with decades of experience that can show how we can implement this mission. And we're not nearly there yet. We've so far had one report by Lockheed Martin and one report by Paragon. We need to have these reports for all our missions. There's many things still to be done. I actually think that I'll hand it over to Barry now to talk about the life support system, and we'll deal with some of the other questions that Andrew and Sydney posed after they come on again. There you go.
Okay, well, thank you, and Dr. Zubrin, thanks for adding me kind of late to this panel. Appreciate it. So first of all, I feel like Andrew and Sydney already gave my presentation, but I'll probably put a little bit different nuance on it. I'm going to kind of go about this maybe a little bit different. I hope it's got some of the facts you guys are looking for. But what I'm going to do is talk about my experience in aerospace, and it may be a little bit different than the average engineer, but I think it brings a perspective to what we're trying to do here. And I should say the focus on our work was assessing feasibility of the initial ECLSS, or Environmental Control and Life Support System, for the base. So in my career, I started out in the bioregenerative world, and we all know Mars One has talked about doing that. We'll talk about later, but we recommend that's not where you start. But that's where I cut my teeth, working with scientists, doing far-out technology development, trying to grow plants to do regenerative life support systems. What I realized was that wasn't going to happen anytime soon. After about 5 years on that program, I said, I got to go do some human space. And so I took a job with Honeywell and got a job on site at JSC supporting the work that goes there on advanced life support. A little more practical work in terms of near-term applications, developing what they called advanced life support systems at the time. Then the career forced me to also start looking at real systems that are flying. I ended up being sustaining engineering manager for Honeywell and for all the environmental control and life support systems they provide for ISS. So I worked that side of the business. Kind of realized maybe Honeywell wasn't in going after human spaceflight as much as I wanted. I tried to switch to another United Technologies Corporation, another ECLSS provider doing station. They still weren't getting it for me. So I went on, took a job at Bigelow Aerospace, second person hired when we opened up the Houston office. That might be a picture of a Genesis module under construction. And moved on from there, went to Paragon, I've been there for quite a while now. And at Paragon, we have a mixture of government contracts and private contractors like Mars One. So again, this isn't to talk about me and my career and what I've done, but in the span of these 20-something years, what I've been exposed to are people, technologies, NASA. I've heard some talk against NASA here. I can tell you Mars 1 or any Mars exploration mission will not be successful without input from agencies like that, like NASA. There's just too much knowledge there. So that has to be brought to bear on solving these problems. So what I'll talk about here is from the feasibility perspective. So this is looking at heritage airspace. So this is the Honeywells, the Hamiltons, the NASAs, those types of what they bring. Well, there's just an incredible amount of knowledge that they have. There's just so much there. There's manufacturing capabilities. There's engineering, the design and analysis second to none in any other industry in the world. And on that knowledge base, I just say I've been a long-time member and supporting the one conference, the International Conference on Environmental Systems. If you go to that conference proceedings and look at it over the years, there's over 10,000 published papers just on life support and thermal control. And it starts to show that depth of knowledge that exists now. And again, in heritage aerospace, incredible record of establishing a foothold in space. We've all seen these, and some of us have been fortunate enough to work on some of these. But what is the challenge with the traditional aerospace world? Well, it's something none of us in this room can control. They're political driven decisions, getting outside of my area of expertise here, but they lack sustained funding. They lack focus on a specific mission. So they don't bring all these resources to bear on the problem at hand. I'll talk about from the Bigelow perspective or the alt space perspective and how this can be used to assess feasibility. Like I said, I was the second employee hired at the Houston office for Bigelow. That was I can't show too much from there, but that was like my take-home test when I applied for the job, trying to say how I'd put the ECLS system together, the ECLS team together to get things going. But what we had was we actually hired a bunch of people away from NASA. They were getting tired. They were getting frustrated, and they wanted to do something different. We hired a lot of people away. So we had a lean team, we had highly skilled, and we had a singular goal, which was go build those first two Genesis modules. We were fully funded at that point. Mr. Bigelow, or Mr. B as we call him, gave us almost a blank check to go do the engineering and do the project management and focus on achieving the mission. And we used applied engineering. We developed products. We didn't develop technology. We took what was out there and we applied it, and we had some spectacular results, that's what I'd say. We launched on Russian converted ICBMs, put 2 vehicles in orbit. These vehicles went through nominal deployment. They were fully functional. And we went from, this is interesting, I always think this is interesting. When I was hired, we had a completely bare floor in the Houston facility, it was a former Grumman facility where they did LEM integration. And in 14 months, we went from a bare floor to building a team to designing, manufacturing, integrating that hardware, and flying the first mission. We had challenges there too. Mr. Bigelow will talk about a lack of the LEO transport capability, and then sustained funding. Once that transportation didn't arrive or show up on scene, the funding dried up. So, from the small business perspective, so this isn't as old as the NASA heritage technology. That's 50 plus years. It started in the 70s, and then really into the 80s, you started to have companies, smaller companies come up, developing technologies, participating in an SBIR program, Small Business Innovation Research. Well, you created a bunch of small companies that came up and trying to do this new space in developing technologies and systems. They're competing all the time. They don't get the big government contracts. So they have an entrepreneurial spirit, they're lean, they're willing to go the extra mile because they have to keep the lights on. And my company is like that. But there's a host of companies like that. This is just a few. These are ones that I work with. And go out and look, and these are the people that are doing the cutting edge now and taking the next steps. And the big aerospace tends to now work with these companies to help let them do the R&D essentially. And again, this is just from the Paragon perspective. I'll just talk about with these small companies, there's some pretty good success stories. For our company, those first 2 pictures there, completely different from what we're talking about now. but taking a Google executive, bringing him up to the edge of space in a spacesuit, letting him come down, do a completely privately funded near-space mission, full product development life cycle. Again, so an example of what 5 minutes, wow. Okay, let me just say this. So there's the other side of what we do. That's classic government aerospace. Those are tubes for the Orion program. This is going back to commercial crew, now somewhere between the two. That's the first new humidity control system to fly in space, when it flies in space, almost since the inception of the human space flight. But the funny thing about that technology, it's based on 40-year-old terrestrial technology that we adapted and used for this space mission. So that's one example of where you're taking technology that exists for terrestrial applications and applying it to aerospace. Yeah, what's going on? So, let's just stay here. So real quick, we've already talked about the ECLSS. This is ECLSS, Environmental Control and Life Support System. I'm not going to talk the details here. We decompose the systems down into major subsystems and then basically put those all together and what they have to do. An important point, and I think Sydney or Andrew mentioned this, there's lots of other systems that are required for the habitat that we have not been asked to look at. And so they're there. Mars 1 has been told they're important, that they need to work on those. Can't leave anything out. Again, this was talked about. We're at pre-phase A. We've delivered an initial report way back at the beginning of this development cycle. And there's a lot of work left to do. Real quickly from the study, system-level design drivers. The essential biggest one is there's got to be water on Mars. And again, I'm just going to hit a few things, but that's almost a showstopper if you want to do sustained habitation early on. There's other ones, electrical power, again, not an ECLSS system. And someone mentioned this in one of the talks earlier today. Without reliable electric power, you can't run modern technology. So Mars 1 has to have solutions there. The pre-crew robotic ops, we talk about this in our work, and that's been again talked about today, and Andrew mentioned it, I think. That's an important detail. Although these systems are going to be designed to be manufactured or maintained by the crew once the crew are there, they've got to be reliable. They have to do the initial work without the crew presence. And leak-tight habitats, I'll just say that's really important. Nothing's going to kill you faster than a leak in your habitat. The Martian environment, thermal extremes, regolith, again, a lot of talk about that today. But there's things also taking advantage of the Mars gravity that is there. You can greatly simplify systems that require phase separation. Landed mass and volume, I'll talk about this a little bit more. This is a concern for us, and we tell Mars 1 what we think we need to put on the surface. They need to come through on the program side, delivering that mass, power, and volume. And if they push back too much, we told Boss if he pushes back too much on that, the development costs are going to go through the roof. And again, he'd have to solve that problem. And then this one, we have talked about this, no new technologies. I really mean this. The systems, the basic fundamental systems that recycle on the International Space Station, the core technologies can be applied, adapted, and optimized for the Mars 1 mission. And we can talk about that more, but we probably will. So the ECLSS attributes, again, real quick, so strictly physiochemical life support. That was our position, and we maintain that. I'm a big believer in bioregenerative. I started out in that, but you've got to ease into it. There's work to be done to develop those systems and have reliability, but no doubt bioregenerative for long term is essential. And one of the other things we talk about is that you've got to have what's going to get you going. Am I really going to be held to 1 minute? You've got to be sure you can build up the buffers, the key things of life, and that's water and the gases. You've got to design for simplicity, reliability, ruggedness. And it's funny, I always talk about minimizing automation to the extent practical. Computers break down. These systems, they're operated. Once we get through the initial phases, the crew will be there to maintain them and operate and recover from failure. And this is getting the ORUs right size, we call it, but getting much different than what's been done on space station, common interfaces. Again, all of this is in the paper. So everything comes with a cost. A lot of that will end up costing you. You've got to pay a price, and it's that mass and volume. And so let me go on here. Just a couple examples on ORU right sizing, I call it. 1 minute. So you've got to take advantage. There's tons of lessons learned on the International Space Station life support. And the things that have been learned are very trivial things can bring a system down. But that's where the work has to happen right there. There's reams of documented issues and problems that have been overcome and solved. And so I'm going to run out of time. So here's the study, just saying there's the mass numbers. People often forget about volume. Volume's a big deal. You got to get it there. You get some advantages by going to inflatables and using bladder tanks and the such. And we need electrical power again. So wrapping it up, are they feasible? I'm not going to say these are caveats, but if we start with the technologies we have and optimize them and improve them as required, yes, we can get. I'm confident to say that's ready. Fully recognizing there's a tremendous amount of engineering and work that has to be done, but it's product development. It's not fundamental science. And I'm talking about the life support system here. We got to accept that there is risk for anything worth doing, and I think we're on board as an industry as a whole that's okay. The Earth-Mars transportation infrastructure. I don't have a check mark next to that yet because that's not my area of expertise, but that's got to be there, including entry, descent, and landing. The business model for Mars One, again, not my area, but they've got to be able to take that business model they're putting together. They've got to be able to take the input we're given, the input that Sydney and Andrew are giving. They've got to take that and they've got to take it to heart and use it as required and modify their plans. And the money needs to be there to fund it. So yes, I see they are fundamental technical. There's no fundamental technical reason the life support system for this mission can't be put in place. And there's 2 question marks there, and I leave those to Boss to work on those last 2. That's it.
Thank you. You can do it from there. We have the hand mics.
Sure. Okay, good. So I think one thing that I want to point out, and that was an excellent presentation, we think that Paragon study is some great work, and anyone here who hasn't read it should really go read it. Excellent coverage of what needs to be done to get to Mars, possible ways to do it, a lot of good research and development going into that. So I think, Sydney, you want to start out?
Okay. So there was the discussion that the Mars One plan is very much in the pre-phase A phase, and the concepts are still being developed. So one of the fundamental questions, and over the last 4 years, the Mars One plan has been sold very clearly as a mission to send people, 4 crew, to the surface of Mars for $6 billion first crew, and first crew landing there between 2023 to 2027, some schedule slips. But the concepts are still being developed. So if the concept has not been finalized, how can you claim feasibility for your mission? You need a concept to do the analysis, to look at the cost, schedule, scope, because as I mentioned before, projects are holistic. You have to look at them holistically. You have to address each of those things. If any of them fails, then your project is at risk of not going through.
Shall we
just go
illustrate
back and
right away?
forth,
I think
or
that's a lot easier.
10 minutes.
Would you like to? Okay, then.
Should we just make it a conversation?
Yeah.
Well, fine. Okay, so yes, you can go. Fine.
So I totally agree, and what Mars One has done in the beginning of our program is we've made a mission design, a very elementary mission design, and we've visited aerospace companies like Paragon and many others, and we've discussed the cost and the mass budgets and the timelines with those companies, and with their feedback, we've come up with the numbers that we present. New reports like the one that Paragon released, where the mass of our life support system goes up significantly, will need to be taken into account in our plan. Our initial mass estimate was a lot lower for the life support system, so that that needs to be taken into account. What we will do, we're not going to do that in the current design of the mission. What we want to do first is have a study performed on the landed mass, because that's basically the building block of the outpost. At this moment, Mars One unfortunately can't afford the study by Lockheed Martin on the landed mass, and I think that is the main challenge for Mars One right now. It's to secure the funding for having those studies performed. But don't forget that it's a crazy enough project that also positive surprises can happen. So it is so ambitious and I think crazy is the right word, that we might actually get a phone call from a billionaire who says, I want to make this happen, I want the first city on Mars to be called Gatesville or Slim City. And that will change everything. Hey? Imagine Mars One having 6 billion in the bank. Suddenly all the big aerospace companies that have some kind of capability of landing systems on Mars will be calling us and making us offers for a reliable transportation system with a guaranteed investment from us, or us as a guaranteed customer for 10 or 15 or however many rockets we need. And so those kinds of things can change everything. So if we need to muddle along for 25 years, then obviously the cost will be higher. If we get a positive surprise like that, then I actually do believe that the cost might be lower. Not by much, but maybe by a little. And we will continue to update our plan with the data that we get. But when we presented our timeline and the 6 billion cost, that was the best knowledge that we had in discussion with the aerospace companies that we talked with.
So I guess then the question would be, you've gotten the first couple reports back, we've done one report, we've talked about several challenges today, and maybe this is a two-part question. Given what you know now, based on what has been presented, what Paragon has done, what other studies have been done, what would you change about the plan? And if I had $6 billion, which I'm sorry I don't, if I gave it to you right now, what would you do with it?
I think that it's very important that we don't start changing our plan until we do have the landed mass capabilities, because it will be a big guess. And we are and we're very convinced that a 2.5 metric ton payload is very feasible. Let's not forget that Curiosity rover landed at 2 kilometers altitude. For practical reasons, we will land at -4 kilometers altitude.
Curiosity landed at -4. Sorry, Curiosity rover landed at -4. That's not correct.
The Phoenix landed at -4.
No, Curiosity Gale Crater is -4.4 kilometers.
Well, let's check that out. Okay. So. And you asked, your second question was? Oh yeah, if I had 6 billion. So the first thing I would do is either to hire a very extensive technical project management team that can investigate all the things that we need, make a good mission design, look at all the interfaces that there are, and then have all those studies performed such that we know exactly what our mission plan will look like. Is it -4?
4,400 meters below Martian sea level.
Okay, good to know. Yep. Thank you. One thing that I would like to say. So we have a very interesting business case compared to the space agencies. I was really shocked actually that our candidates think that they will be followed 24/7. Please no. What I think is that our candidates will be very proud of what they do, and they will want to share a lot of things like they're doing here and like they're doing on schools. But they are always in control of what will be going to Earth, because they are in control, right? We can't send the Marines if they don't do what we tell them. So, but on the business case, I have met with many investors, and all of them see the business case. They don't worry at all about the business case, and they don't even worry about the mission becoming twice or 3 times more expensive. What our investors worry about is 2 things. Technical risks. So what, for example, there's the 10%, 5 or 10% chance that a rocket explodes. What if the first unmanned mission fails? Fortunately, we can insure the first unmanned mission because it's a copy of the InSight mission. So it might be very feasible that we insure it and that we can try again. But the other thing that they're very worried about is that someone else beats us to it. But they're not at all worried about the business case. So what I present to investors is that just the media side of Mars One can yield 8 times what the Olympic Games are worth, which is about $36 billion from today until the first humans on Mars. So that's a good return on your investment. Doesn't matter if it's $6 or $12 billion investment. And then there's the intellectual property development and all the other things. One of a space funeral company approached us and said, if you're going to Mars, we want our customers, they send small amounts of ashes on missions to orbit or even to suborbital. We want our customers to be part of that. When I came up with the business case for Mars One, I wasn't considering the funeral business. So there's so many new business cases that come along, and investors are really into that. So they've literally said to me, the cost is not so important to us. It's about, can you guarantee that this will happen?
You need spares.
Should use solar panels. We can share.
Okay, so you mentioned that you thought that our study found the Mars One mission plan to be feasible. However, the big takeaway from our study is that based on the Mars One mission plan, as claimed on the website and as you have advertised on several occasions, is fundamentally unsustainable because the cost grows over time as you increase the number of people on the surface of Mars. You've also said that all the arguments you've said so far were regarding the 6 billion figure number, right? But when you launch people, if you do that is, to Mars one way, you have to resupply them every 26 months. And that incurs more and more cost for the rest of their life. So how do you make the business case for people who are investing in this that the cost that you're incurring by making this decision that they need to be resupplied every 26 months for the rest of their lives, which is several $1 billion, that just doesn't close when we look at this. And this further doesn't close when you add more and more people.
And on top of that, you mentioned the technical risk. That's kind of, I guess, curious that an 8-time return on investment for a risk that's something that has very, very many myriad challenges ahead of it and incurs a cost obligation unless you're willing to stop resupplying the colonists, which I assume we aren't, for a very long time. I'm curious just how that all closes.
Hey, and boss, I'm not going to pick on you, but I've asked some of the same questions, and you've talked to me about the business model side of it and how it pays off. And it took me a long time to get my head wrapped around it, but I think you should talk about that. And for me, I'll just tell you, the takeaway is, I'm going to tell you my opinion. You don't have to launch a crew every 2 years, sorry to the candidates, for this mission to be successful. If it's every 4 years and every other time in between is a supply mission, what I understand now, that's not going to change the business model, the side of where the funding's coming from. So I think that needs to get explained a little better, because it took me a long time to understand it.
Yeah, that's right. So we hope to send humans every 2 years, and we do still believe that is feasible. But if we can't, for whatever reason, it could also be that when the first crew goes, the hardware for the second crew goes with them. But if one of the systems breaks in such a way that they can't fix it, then the second crew will go 2 years later. That's already part of our plan. So if we can't send the crew for a different reason, for example, financial reasons, that's also something that we can accommodate. So you had two other questions, one about the return on the investment. Actually, the return on the investment is much higher than 8 if you invest early and much lower than 8 when you invest late. It's always like that. So the first investor that comes on board will finance, we're currently looking for $15 million US, will finance the build-up of a very good team, so a very big expansion of the team that is actually capable of starting to roll out this program in a lot more detail. And financing all the studies that we need to do, and building the simulation outpost where we need to start training the crews. But after that is all done, and there are these very detailed reports from the aerospace companies that we're talking to, then the risk will go down, because there's more known about the project. So the next time, the investors will pay more per share, so they will get a lower return on the investment than the first ones coming in. That's how it always works with companies throughout their development. What's very important is that something that's not a current existing technology, but that's a very important part of the Mars One plan in the long term, that we need to start producing things on Mars locally. So one of the things that I would really like to do as soon as possible is to write out a request for proposals from all kinds of I shouldn't say institutes, entities, so it could be schools, university teams, whatever. We want to see proposals for how do you build a habitat with local materials. If I really recommend to you, one of the coolest videos I've ever seen on the internet is if you Google glass sintering, there's an artist that 3D prints sand. It's so cool. So I don't know if we can build a system like that on Mars in 10 years, but there's no real reason why we couldn't. So if you can start building your habitat, so your habitable volumes on Mars, and maybe send a bladder to make them airtight from Earth, that will save a lot of mass already. And in that way, we need to start implementing smart solutions. And there's carbon molecules on Mars, and there's hydrogen molecules on Mars. So in principle, if we have energy, we can make plastics. And so all kinds of things are possible, but I don't think we need them for the first 2 crews, but I do completely agree with you guys that we need to have some kind of local production method to sustain a group of people that is larger than that. But do you think that is technology that we cannot develop in 20 years?
Well, I think, again, it depends on the funding and the schedule, so those two things are linked. So NASA, actually the challenge you just described, NASA has that challenge ongoing right now. There's a 3D printed habitat challenge exploring how to use Martian regolith. So I completely agree. These are the kinds of things, and this is in general as far as how to move the Mars exploration, Mars colonization, Mars settlement plan forward. These are the kind of problems that absolutely need to be solved. And maybe it'll work in 20 years. Maybe there will be some breakthrough tomorrow and someone's already figured something out and we just don't know about it yet. But there's all this uncertainty and there's a lot of cost going into developing that capability. So I guess one question that I'd have that I think has been a part of this whole discussion and a part, I think, since our study came out is the question of really the difference between a new technology and a new system. Because that's something where I think maybe there's some miscommunication. So you said that a new technology we don't need new technologies, and I'm paraphrasing a little bit, because the processes are understood. There's no fundamental reason that these things can't be done, right? So then the question would be, when Goddard fired a liquid rocket in 1926, why didn't we immediately go to the moon? Why didn't we immediately go to Pluto? When Sir George Cayley described the physics of flight in the early 1800s, why did it take 100 years for the Wright brothers to do it? So I think that's, I guess we find the cost element to be not just until understanding the process, but making a process into a usable, feasible system. So I'm curious, what are your thoughts on the difference between a technology and a system?
And maybe I can, from the life support system, I can talk to that a little bit. So your analogy about the rocket development, where we are in the development of life support systems and those core technologies that do the water recycling, that do the air revitalization, we are not at the equivalent of Robert Goddard versus an Apollo. Again, this was my point. And just to back up again, the no new technology, what it really means is we understand the physics, we understand basic materials. With the physics that we understand and know, and we've turned into engineering solutions, that's where we are. We don't need to create a new material. We don't need to, there's not some fundamental physical process we don't understand that has to be developed or perfected. So, but then going back to the hardware, so the systems that fly International Space Station, we all talked about, they're optimized for that mission. And again, they were going, reducing crew time at the expense of mass, because we had a space shuttle at one time flying regularly. And that's a completely different case for long duration life support now. And so that's applied engineering. And again, it's not that there's not hard problems to solve, but that's what people like me and like you guys, that's what engineers are good at, are solving problems like that, coming up with simple, efficient solutions. So when you're going to go do this mission, when BOSS gets the funding, you're going to establish those requirements. We call them driving requirements on our report, but you're going to go far beyond that. You're going to develop a clean, crisp set of requirements that we designed to. And you'll find that if you build upon what's already been done, you can make those machines operate. You can solve so many problems that they've experienced. And again, I encourage people to look at like the problems that have happened at the International Space Station. Some of them are really simple, and you're like, oh, why didn't we think of that? There's lint that clogs fans, and no one thought to put a filter there. There's dust that accumulates. There's these very simple things that have happened, but we've learned those lessons. And so it's like, in this case, it's like any other industry. You learn from what's gone before. So those lessons can be applied, and you can get to the reliability numbers we need. You can get there. But what you don't want to do is start developing new technology at this point. If Mars One was to go down the path of waiting for the next new technology, again, some interesting talks here I heard about today, using the chemistry that exists on Mars now to produce carbohydrates and things like that. You won't get there. You've got to start with what you know.
I'll add one thing, or will I? I just had a thought that I wanted to add, but I think it slipped. It slipped my mind. I'll add it later.
Yeah, go for it.
So the topic of this debate is Mars One feasible? And so we presented a set of slides that summarizes what you have stated that you will do, the cost, schedule, scope of doing that. We don't disagree that life support is a solvable challenge, but these projects, they're very complex. It's a house of cards. If any of them don't work, then the whole thing fails. And so we could talk at length about ideas for potential technologies when they might come into play. But you can't assess the feasibility of a program unless you have a concept, unless you have a cost, schedule, scope, and that you've justified for it. And you've readily admitted that your concept is still changing. So if your concept is still changing, you still don't know what technologies you're going to allocate your schedule and your funding to develop. So we just haven't seen any arguments to justify that it's feasible. Do you want to add to that?
Yeah, and I guess one thing that's kind of important to note from this panel and from the previous panel as well, and from a lot of other discussion that's gone on, we've seen a lot of excellent arguments for going to Mars. And we have no disagreement with that. That is our goal as well. That's why we're spending all these years in grad school. But to us, that means sort of looking these challenges in the face, saying, what do we need to do? What's kind of the hardest thing here? What are things that we need to be able to solve? And so I guess our question is, we all agree that Mars is a valuable goal. It's where we need to go. And I think we all agree that we'd rather go sooner rather than later. But the question that we're wondering is, why the Mars One plan as it has been presented? And if it's going to change, I mean, the plan as it's currently been presented to us is infeasible, and that was a presentation we've made. The question would be, what changes in the cost, what changes in the schedule or the scope of the plan will be made to make it feasible? Because the one that's presented right now, it seems, is not feasible.
And if you're still developing concepts, you don't really have a plan. A plan is you've got your work breakdown structure, you've got your funding allocated, you know what steps are moving towards your goal. So again, the question is Mars One feasible? Can you land 4 people on the surface of Mars, one-way mission, in 12 years for $6 billion?
Did Kennedy have a plan? He didn't have the technology. Look at the slide that I showed you. Everything changed. We are presenting something that is feasible. There's nothing that cannot be done. And I agree with you guys that we are not certain about the cost yet. And I agree with you guys that the cost might be higher. And I certainly agree with you guys that our timeline might slip again. But are we failing if we land humans on Mars in 2030 or 2032? Is Mars One unfeasible if we land in 2032? I don't think so. So one of the important differences between going to the moon or going to deep space and going to Mars is that you can test your systems for a Mars mission with relatively high fidelity here on Earth. So that's why I think our simulation outpost is so important. At first, our simulation outpost will be built to test our crews, to see if they can deal with each other, basically, and with all the challenges that we will throw at them. But we will start adding the technologies that we want to actually send to Mars, with more and more realism built into them, such that we have a pretty good understanding when they do depart, much better than systems that are sent to the ISS, because there is, as we all know, a zero-G environment. So that I think helps Mars One's plan in relatively affordable testing, because we can do it on Earth. So it's an ambitious project, and there's a lot of problems that still need to be solved, but the rockets are not the problem. The transit is obviously not the problem. Landing on Mars, if we have right now the estimate by Paragon is 7.5 metric tons useful payload. If we have to break up that system into two, at 3,750 kilos, I've talked to several experts from NASA. They say that they can do that with the current method. So the heat shield, the parachute, and probably not the sky crane, but retro rockets. The life support system Barry has talked about, I think that suits are actually one of the biggest challenges. So creating a suit that will serve the astronauts for a very prolonged period of time with acceptable repair and acceptable EVA time, because you don't want to spend your life on Mars only inside. So definitely a lot of engineering challenges, but no fundamental things are needed. And our plan is not designed to, for example, you mentioned the rover needs to do all these things. That's not necessarily the case. We might have 2 rovers that do separate tasks, or we might have 3 rovers that do separate tasks. We don't know that yet, but we do know that lifting something is possible. And we do know that moving sand is possible. And we know that. We can test these systems on Earth because we have a gravity environment, and we can design them, we can build them, we can test them, and we can make them better until they work.
Okay. I want to interrupt, okay, because we're about to transition to the next part. The next part of this. Which is going to be the questions. Now, this debate has actually attracted some international attention, and we've had some questions sent into us. And in particular, there's been a group of 5 questions sent here from a veteran aerospace engineer from Germany, Jürgen Herholz, who's worked for 3 decades in every European manned space program, from Hermes through the ISS. So he has a number of questions. I just want to ask two of them, and they're both directed to Mars 1. The first is, which I think is pertinent, is when does Mars 1 intend to propose a Mars 1 mission, technical and implementation concept in credible detail, taking into account past technical and program experience?
Can you ask him back if he has 15 million? So it's when you start a company. This is the second company that I start. I started a wind energy company. I co-founded it with a technical partner. I was the general manager of that company, and we started looking for investments. And all the time you think that it's just around the corner. You talk to a new investor, you have really good discussions, and for whatever reason it doesn't happen. And that's just a fact of building a company. How many people here in the audience run their own companies? How many are raising money for their companies? So you guys know how difficult it is to raise money for your company. It's difficult. It's unpredictable. You can't control it. And once you have your funding, then you start to actually be able to control things. And at this moment, actually, we do have quite a lot of time. We had to announce a delay in January. But because of how the planets orbit the sun, that actually gives us 2 years to raise the money starting last January. So we do have a reasonable amount of time to get these things on the road. So my estimate because it's basically funding what he's asking, my estimate is that we will secure our required funding. If I'm optimistic, I would say in the next 6 weeks. If I'm more realistic, I would say we can do that before the end of the year. So then 1 year later, we can present a much more detailed version of Mars 1's plan.
All right. And then just one more of his many questions. He says, needed on Mars, in addition to mission return, which I guess in your mission plan there's not, but needed, I think that is pertinent, is construction equipment, mining capability, transportation means, repair capacities, facilities for the production of food on a sustainable basis using Mars resources. This requires new development and long-term testing on Earth and in space. Therefore, what are the plans of Mars 1 to develop and test a sustainable and self-sufficient infrastructure on Mars, providing Martians with acceptable conditions? In other words, how are you going to test all this ancillary equipment on Mars in advance of the crew?
So that is where we're very fortunate that Mars is actually a planet and not space. So Mars does have gravity. And the simulation outpost is a crucial part of our plan to start implementing and testing technical solutions. But everything will be step by step. So, for example, it's our goal to start growing plants on Mars as soon as possible. And in this study, it was not taken into account by Paragon yet. But we're because you need to develop the base without plants, because there's no humans yet to grow your plants, and because you always need a fallback solution in case, for whatever reasons, your plants are not growing. But growing plants is crucial for psychology, for sustainability of the funding of the mission, and we can test that with high fidelity here on Earth. But it doesn't have to be immediately with completely closed recycling or with Martian resources. You might, for example, take all the nutrients from the plants from Earth, which is a very small percentage of the total plant. Maybe you add the nitrogen from Mars because you have it there. It's relatively easy to produce, what's the fertilizer? But you can keep adding Earth-sent nutrients for your plants for a couple of years. That's acceptable in the mass budgets. But at some point in time, of course, can someone switch the button again? Because I'm... At some point in time, you do want these technologies, but they can be gradually developed over time. And as I said, what helps immensely is that we will have a simulation outpost here on Earth where we can test the systems in a relatively high fidelity environment, namely a gravity environment.
Okay. Does the MIT team wish to take a couple of minutes to respond to Bas's most recent remarks?
Yeah. So regarding the first question, in June of this year on Bloomberg TV, you said you had executed a detailed technical feasibility analysis. So my question is, what is that analysis for the mission? And if the question is, when will you present the analysis, and you've stated that you have one, when will that one be presented?
There's TV and there's science conferences. As the CEO of the company, I always have to balance between how I phrase things. And our initial study has been a good investigation of the possibilities of sending humans to Mars, but not what NASA would call a detailed feasibility report. But our investors do. And when I show what we have done to our investors, that's what they would name it if I didn't write the name on it myself. So it's a matter of perception. For an aerospace engineer, there's very strict. They're right here actually on various slides. There's a very strict timeline in when you call it a detailed design. That's not something that investors use. This timeline is not something that investors use. Investors have a completely different understanding when you say that word. And Bloomberg is not the kind of channel that scientists watch. It's the kind of channel that investors watch. So there I'm talking to an investor audience.
I'd like to address some of the comments that you made earlier. So you asked us, when Kennedy announced Apollo, did he have a plan? So we didn't have a plan at that time, but people had been doing serious technical studies for a long time. Within a year, in 1962, the lunar orbit rendezvous decision was made. So a year after the plan was announced. So Mars 1 has been around since 2011. So, and it's 4 years, 4 years, sorry, later. We still don't have a technical plan. So that's my first point. Yeah.
NASA has been promising us a manned mission to Mars in 20 years for 45 years now. So I think we still have a couple of years to go before we're behind on that schedule.
So I'd like to point out that bashing NASA does not prove the feasibility of Mars 1.
Sydney, take 1 minute to make some remarks, so then I want to have some
Okay.
questions from the floor.
So I'll reiterate the finding of our study that one-way missions to Mars with increasing crews grows unsustainably over time, and then the cost grows unsustainably over time accordingly. So the comment was, you can delay your missions for another synodic period, but we've done analyses on that, and that doesn't stop that growing cost over time. So we still don't see how the Mars 1 plan, as stated, becomes sustainable over time. So the question is, how willing are you to change the scope of your mission, to de-scope it from one-way missions to maybe something less, like an orbital mission or something like that, given the real-world constraints and difficulties of cost, schedule, scope?
I would first like to comment on bashing NASA. I fully agree. As Barry has already pointed out, it's only possible to even consider going to Mars because of all the great things that NASA has already done. So let's not forget that. But our delays are not caused by technical limitations. They're caused by funding limitations. There is no reason why we could not have those technical reports if we had adequate funding. And well, funding is difficult. And when you start your own company and you start to raise money, you will find that funding is always difficult and will always be difficult. So the answer is to your other question about sustainability of increasing crew size. I do think we talked about that. It's producing things locally. So we will need to develop the systems to produce things locally. And at first, simple things. Actually, we do already, of course, like water, nitrogen is already part of our plan to produce locally from the start, oxygen. And we will need to build on that capability of producing things locally over time. And if our first crew is scheduled to go in 2026, landing in 2027. The second crew landing in 2030, because then the 26 years actually goes over the December. 2030 is a long time away. If you look at what 3D printing has achieved in that amount of time, you can see where things are going. So the question is, can we produce on Mars a ink for your 3D printer? And I think that's much more an energy question than a technology development question. I mean, we can produce plastics already for 3D printers here on Earth. I am convinced a lot of that is now done from oil, so it's breaking it down, but there's no reason why you couldn't do it the other way around.
Okay, but by the way, Bruce, could you cycle the lights, please? Okay, thanks. All right, we're going to take questions from the floor. This lady over here.
Hi, my name's Valerie Sharp-Geisler, and my question is, or thought, certainly the first couple missions, first couple crews that go are going to be there to set up sustainability of their very continued existence. But after you have your first few crews there, aren't governments and other businesses going to be banging down your door to pay your crews to go to work on Mars for them?
Yeah, it's one of the business cases that we actually considered 4.5 years ago when we started Mars One, but it's a long-term one that can't give us any return now. I think that when Columbus sailed across the ocean, his business case was a shorter route to India. And he actually basically founded the richest country of the world, where most of the innovation is coming from. He didn't really expect that, I think. And I think that with Mars it's the same. Mars is the same. So that's definitely one of the possibilities. How about, and once there's humans there, it will be so much. My CTO never allows me to say easier, so I'll say less complex. It's so much less complex to send a small rocket with 1 or 2 kilos of Mars rocks back. And imagine the value of Mars rocks. And now, just from the scientific community point of view, you're thinking, but imagine that we catch momentum and that people start believing, holy cow, these people are actually going. Imagine the excitement that will bring in people, and imagine how much people will want is it a cufflink, right? A cufflink with a grain of sand in it, a necklace with a grain of sand from Mars in it. The people going there will be heroes for everyone on the planet. The value of anything associated with Mars will increase exponentially. And imagine, I don't remember who pointed out that it's just €1 per person on the planet. Well, not everybody has €1, but there's already people who donate $200 per month to Mars One. $200 per month, and that's in our current phase where we have. Well, and we've had good accomplishments, but of course we're still really in the beginning of our project. Imagine how much more of these kinds of things will occur when we achieve more. So I think there's not hundreds, but thousands of business cases for a human mission to Mars that we can't even imagine yet, like funeral services.
Does MIT wish to spend a minute to answer Bas's remarks?
Well, one question that I would have, you talk about this great interest.
What, do you want to answer his remarks?
Well, this is in relation to those.
Okay.
So in relation to the idea of developing this enormous interest and this enormous sustained interest, because your costs are sunk for the rest of their lives if they're the ones to go. I don't know how long you guys intend to live, but presumably a long time. The Apollo experience was we landed on the moon and interest dropped rather sharply until Apollo 13, and then it went up again, and then it went back down again, and we're not on the moon anymore. With the International Space Station, it's this wonderful object in orbit, and a lot of people really don't care. Like, oh yeah, we got a space station, cool. At what point, I mean, there's a concern that it becomes, yes, there's this peak of interest. We've landed on Mars. We've lived on Mars for 6 months. We've made it to a year. Oh, those guys are on Mars. Yeah, we have people on Mars. Like, the interest starts to decay over time. So in your business plans and in your considerations for all of this, how are you going to deal with that factor?
Well, as I said, there are many business cases. So intellectual property is one of them. Mars One will always make sure that we become co-owner of the intellectual property of the systems that our suppliers build for us. And we were already doing that for our follow-up contract with Lockheed, and that's perfectly acceptable for them. But that's just one. So then there's funeral services, there's research for other space agencies, and there will be many more of those kinds of business cases. But just the media business case, so the media exposure business case, sponsorship and partnerships, I have talked to many media experts, and they all confirm that this is something that people will be interested in for decades, because it is not, it's not a couple of test pilots that were picked for reasons that nobody really understood. This is an adventure where we take people along for the journey, not as Big Brother, but much more like the Olympic Games, which is repeated every 2 years and draws huge attention every time. And we don't need an Olympic audience all the time to finance our missions. And we need one Olympic event worth of media exposure per 2 years. So that's, the Olympic Games are 3 weeks, 2 years is 100 weeks. So we need 1/30th of the interest for the Olympic Games on average over the year to fund it with only the media business case. 1/30th. That's really not a lot of interest. And that's, media companies have said to me, we develop formats. And we don't know if they will be successful, because otherwise we would only produce successful formats. But all the media companies that I talked to, it's about 4 major media companies, they all said this is the exception. This is something, it's so inherently interesting to humans. Exploration is coded in our genome. Either you want to go and you're jealous of the people that are going and you want to live the experience through them, or you don't want to go and you're terrified of the idea and you're even more interested in it. And that is something that will be, according to these companies, sustained for a very long time. I actually, when I came up with the idea together with Arno of the media revenue, we talked to a very famous Dutch media expert, and he said, for decades and decades. We went home.
Let's wind it up. I want to get more from the floor.
I'll wrap it up really quickly, but
Okay.
it's important. We were driving home shouting, yeah, we have a business case. And then we came up with the same conclusion. We went back to him and asked him exactly the same question. And that is what he said, and that's what all the other media companies that we've talked to said.
Good. Now, I want to take questions from the floor directed to one team or the other. They should answer in a minute, and the other team should reply in a minute. Okay? Who wants to throw one at the MIT team? Over there. Right here. What? Over? Do you want to throw one at the MIT team?
Yeah.
Good.
I wanted to address a part in your study that I don't think we talked about a lot, which was it's kind of the morbid part about crop production and oxygen and carbon dioxide. And I think you guys found there's like a catch-22 situation that there wouldn't be enough crops, or the crops wouldn't produce enough oxygen, and if you had more crops, it would produce way too much oxygen, which might lead to like a fire risk. So I wanted to talk about that a little bit more and what the problems were associated with that.
Yeah, sure. So there are a couple of dimensions to that analysis. First, we were testing the claim that Mars One said that they will only use 50 square meters to sustain 12 people, 3 crews of 4. We did analysis and found that they actually need 4 times the amount of crop growth area to sustain a third of the people, and that's really, really optimistic, assuming best case scenarios for plant crop growth. Now, with regard to your imbalances in the gases, comment, that's been known within the life support community for quite some time, that the amount of CO2 produced by humans can only sustain about half the crops that you would need to keep yourself alive. And so the point of that, and that was an analysis that was intermediate, that was not the biggest finding of our study, and we've emphasized that on many, many occasions, was that if you're going to grow crops, you need a means to separate oxygen from your atmosphere selectively to manage that imbalance, basically because crops and humans have different atmospheric requirements. However, in addition, our study found that over the life cycle of the program, in that study, we found that growing crops was more expensive than carrying food along because of all the infrastructure required to sustain that. But since then, we've been, did you want to talk about that?
Well, I guess like the main issue with the crops is if you have enough crops so that your oxygen and carbon dioxide are balanced, you don't have enough food. If you have enough crops to grow all your food, then your oxygen and carbon dioxide aren't balanced anymore. So I think that's one thing, we're not saying this is impossible to solve. It's just an additional consideration that I think you would note as well, that these are known in the biological community. So the issue there with the fire risk, for example, is we were trying to test the Mars 1 plan as described, which was grow all the food for the crew using crops. And if you do that, you have this oxygen problem where the fire risk becomes large.
So the important fact, I'll wrap it up real quick. So the important point from that finding is that you need more crop area. If you were to go with Mars 1's assumptions and more technologies than they had originally claimed. And as I mentioned earlier, if you change your scope, your cost and schedule need to adjust accordingly.
Okay. Does Mars 1 want to answer those remarks?
Yeah, hey, I'll talk to this one. So we've talked about this a couple of times, guys. To the question that was asked, the main issue was, and I know you said it wasn't a main point, but at the end of the day, the result that you came up with, that the crew was going to die, that is what the media latched onto. And it was some very simple assumptions you all made, and we've talked about it. We know what you did, why you did it, in terms of running the model. But the point is and this was another slide I was going to add if I had time. There's a tremendous knowledge base out there. In the 90s and 2000s, a lot of work was done on bioregenerative life support. There's I can give anyone the paper that lists over 680 publications. There's straightforward ways you go do this crop production. You don't plant it all at once. You combust the inedible parts as you get that CO2 back to do the balancing. So there's a knowledge base out there to go do that, and that wasn't included in your model. And that's a good lesson. I don't know if you guys admit it, but that was a lesson that was learned the hard way. When you build a model like that, you you made assumptions, and I know you made those assumptions, and maybe you didn't get the feedback you were looking for from Mars 1 about the assumptions. But you make bad assumptions, you get an output from a model, and you get a nonsensical output. I mean, we all know this. No one's going to vent the atmosphere on Mars to maintain CO2 or oxygen levels. No one would design a system like that. It's nonsensical. But unfortunately, that's what the media picked up on. And I know you guys know that's nonsensical. But that's what they picked up on. And it's unfortunate that happened because it takes away from the rest of the message and the rest of the work. And it was tough. It was.
Yeah, I'd like to ask a clarifying question because I'm surprised at the statement. If you grow enough food to feed the crew, then you're CO2 short, is what you said. How can you be CO2 short on Mars?
So you're CO2 short without an additional option, which we implemented.
Like opening the window.
Yes, which we implemented in the model. And then the other problem comes up because the crops create the oxygen. So you are CO2 short and oxygen long, basically. It's an imbalance. It's a cycle.
Okay, but to be clear, CO2 is a readily available resource on Mars.
Yes, and we implemented it in the model.
You don't have to only get it from respiration.
Yes, and we implemented exactly like you say in the model. We're agreeing with each other.
Okay, let's take another question. Who wants to throw one at Mars 1? Over there, Terry.
At Mars 1, when these guys talk about sustainability, and these guys talk about infinite spare parts accumulating over time, it seems to me that if I were you, I would think about how you refurbish a spare part, because when something goes bad, that doesn't mean it's totally bad, and doesn't mean you necessarily have to throw that mass up from Earth. So you need to look at your systems, I would think, and think about how you can refurbish parts so you don't need all those spare parts coming as mass from Earth. And there are lots of spare parts, I think, that are going to be in that category. So this brings me to a more general question. Are you planning to both perhaps redefine, but at least start implementing the notion of technology readiness levels for each of your subsystems and letting people know where you think those TRLs sit and letting people give you feedback as to how to improve them, testing in plumb book vacuum chambers, stuff like that? What are your thoughts in these directions?
Yeah, absolutely. So all the lessons learned in aerospace so far, we will need to use them, and technology readiness levels is definitely one of them. So our mission is not currently in a phase where we can say these are the levels for these systems, because we're not there yet. But of course, that needs to be done. And either hiring a really good technical team that can start looking at these problems from the reports of the suppliers, or another option might be hiring a third party, so to say, technical management company that will actually oversee that part of the business for us, is very high on my wish list. You want to say something, Mary?
Just real quick, well, to refurbishment and reuse, that's definitely, we talk about that in our report. That's essential, and you've got to rely on that. The other thing is, I just say that it's when you're doing technology maturation like this, and you have a program that's ongoing, and you can't predict exactly how the system's going to be run and operated, and how they're going to be run differently. On the International Space Station, one example is they had expired saline solution, right? What they do, they squirted it out on towels, let that evaporate, and then condensed it on the condensing heat exchanger in the spacecraft. So it's just as an example, but the crews are going to get very innovative. And again, I'm not an expert in this area, but human innovation and how you solve problems when you have to solve them, that's one thing human beings are really good at. That's what people always talk about, the advantage over robotic missions. That crew, when their life depends on it, is going to be very inventive in developing solutions.
Does MIT team wish to respond to this?
So you bring up an excellent point, and this is actually my dissertation topic. This is my dissertation topic. This is looking at level of repair, going to lower levels and refurbishing. You know, if you lose a gasket, you don't throw out the entire spacecraft, right? So the question becomes, where do you implement that lower level of repair? How much massive tools and diagnostic equipment do you need to be able to seek out the failure? How much crew time do you need to be able to seek out the failure? How much redesign does the system need to be designable in that system? And you still there is some piece that you need to replace. And that's where things like with 3D printing, something that's particularly interesting to us, that opens the possibility of maybe closing the loop on spare parts, where you can grind up the old one and make the new one, just like yesterday's coffee becomes today's coffee on the ISS right now. And so basically, like, you're absolutely right. These are all things that need to be done. And all that we're saying is it costs money to do those things, and it takes time to redesign these systems, and there's a lot of uncertainties that come up when you look into these questions. Another point that's kind of related, that's a little different from the sort of random failures that were brought up earlier, is the limited life components, some big ones being filters. Filters can get clogged or burst or other things like that. And there's some things that right now, we change every 3 months. There's other that are about every year or so. There's a range of things. But those are not necessarily something that I can refurbish and put back. There would be a significant design challenge incorporating to refurbish some of those components depending on the function.
In this slide, I'd like to throw a question at the MIT team, because you did these studies showing the difficulty of maintaining reliability of systems as the number of systems multiplied. Did you take into account the fact that there are people there to fix the systems when they fail?
Yep. So we assumed that with 10 years of training, the Mars One crews were perfect mechanics. So the risk numbers that were presented there was only the risk that you don't have the tool you need to accomplish the job. There's additional risk that the maintenance goes wrong, or that you don't find it in time, or that the design was wrong, or that there's something about the Martian environment that you don't understand. So as far as in our models, we did take that into account to say that we're assuming that you guys are really, 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 really good mechanics who never mess up.
All right, from the floor.
There will be.
How about, you have someone? Okay, go ahead.
Yes. Good evening. My name is Karen Elise Warmack. It's really an honor to be here. And I have a comment that's directed to Mars One. I'm so proud of you. I'm so proud that your faith supersedes the money you know is necessary to have. And I remember listening to Zig Ziglar, not personally, of course, but I heard one of his recordings where he shared how Henry Ford told his team to go and build the V6 engine. And they said, no, we can't do it, it's impossible, et cetera, et cetera. And Henry Ford knew in his thought life that it could be done, and he had the team that had the mind to manifest it, and they did. And so I really appreciate the way you know what you want. You may not have all the answers, and I really appreciated the way you said, you spoke about surprise, positive surprises. I really appreciated that because children may be one of the answers with your funding. And I say that because I'm also going to be a fast-track speaker on Saturday evening, and I will be presenting the adventures of Percy and Missy Beyond Earth's Sky to Mars, where these girls, cat girls, do go to Mars. And it's going to be my third published work in a series of not less than 15.
Okay, we want to take
And I'm
questions
excited
to
for you
the
hear
speakers.
that, and I thank you so much for your faith in what you're doing.
Thanks.
Okay, thank you. Who has a question for one of the teams, preferably a sharp one? Sharp? Annoying? No, not annoying. Sharp? All right, good question? Yes, all right.
In terms of the business model with the media companies, what is the tipping point, or what is the underlying hurdles that media companies are looking for before they'll underwrite the larger checks for the thing? So when they say to you, okay, NBC say, we will jump in when XYZ is performed, what are they looking for? What's the tipping point?
We probably actually won't do that with media companies. So we'll wait quite long until things are really becoming definite before we start selling rights to media companies, because media companies are not investors. They're not used to dealing with risks. With sponsors, for example, partners/sponsors, it's already a little bit better. So, for example, let's see how I do this without disclosing confidential information. I'll keep it. I'm sorry, I have to keep this a little bit fake. It's a company that's currently not interested in doing something with Mars. There it goes again. But they're very interested. They want to do something with our first unmanned mission, and they said, for example, as soon as you have a fixed launch date, so basically finance the mission, even though it will still need to be completely constructed, then we're very interested in paying the upfront fee for the sponsorship and partnership. But in principle, all the upfront money is going to come either from investors, which is what we're currently very busy doing, because investors are very good at assessing risk and the upside, or from people that are already donating to Mars One now, just because they think it's cool.
All right. Someone with a sharp question for one of the teams.
Hi, so you've presented the Mars One project as unfeasible in its current form. Oh, sorry. The MIT team.
Probably us.
Yeah.
Okay.
So, my question for you is, what would it cost in both time and money to make the Mars One mission feasible?
Fundamentally, so to make the Mars One mission plan, as stated, growing crews every 2 years, or that's still subject to change. I think we all agree that we need an in-situ manufacturing capability. We need the supply chain on the surface of Mars. So then the question really gets reframed to how long will it take for us to develop that capability, and how much will that cost? And so that also begs the question, why don't we develop that capability before we ever send crews on one-way missions to Mars? Why are we sending them there first, and then hoping that this capability comes to fruition, which it may or may not? It's a very uncertain thing. And then relying on the fact that that will come and be deployed to make our mission sustainable. So I guess my position, I don't know if you agree, is we should get all the technology developed before we go. Okay, so that's the first option, if you want to go with Mars One plan. The other one is you de-scope. Instead of doing one-way missions, you do less demanding missions. You could try to go orbit around Mars and then come back. And that's going to be a lot easier because we don't have the EDL capabilities. And that's just one suggestion. I'm suggesting that's what they should do.
What would that accomplish?
Right, that could be a precursor. But all I'm saying is, to address those issues of infeasibility, you have to relax those cost, schedule, scope dimensions.
So I think that because it is also a possibility to send 4 or 8 people and sustain them, which is feasible, as long as you don't start increasing your crews too much, that's a feasible solution. I think that our crews will be willing to take the risk that they're going to spend a number of years with just 8 of them. If they weigh that against the odds that we cannot develop local production facilities. I really want to remind everybody in the room again about President Kennedy with no technology existing at all, nothing existing. And 8 years later, we land on the moon. And one thing I want to add, I consider, and I know that not everybody, including the person sitting next to me, will agree with this, I consider a Mars orbital mission more difficult to accomplish than a Mars landed mission. Because, I will explain it, because you're looking very worried. For the same reason that I consider a moon mission more difficult to accomplish than a manned mission to Mars. It's because of, as you have very clearly indicated, you need to finance it too. And I think that the financing for a manned landed mission, and that's also what Robert was kind of pointing at, I think, is easier than, so for example, if the orbital mission would be 3 billion and the landed mission would be 6 or even 9 or 12 billion, I think it's much easier to finance the landed mission than the orbital mission.
Let's get another one from the floor. How about over there somewhere?
For Mars One, do you discuss with your potential investors the risk of some crew members getting killed? And if you do, what is their reaction to it? If someone gets killed or if the first crew members don't make it, is that the end? How do you recover from that?
That's a really good question, and yes, of course, that's part of the risk that I explained to them. So sometimes the investors or potential partners are really naive about the risks, and I always immediately lay them all on the table. So first unmanned mission failure, first manned mission failure. We need to, you can only achieve a good relationship with an investor and secure an investment if you're completely transparent in those kinds of things. So we do, and what I tell them is how we plan to mitigate those risks. So for example, the first unmanned mission we can probably insure. The first manned mission, it doesn't matter if you can insure it because you have a loss of a crew. How we mitigate that risk to the extent possible is by landing the crew in a system that has been tested, similar, that looks a lot like the system that has landed all the cargo missions. So building on a track record. Neil Armstrong and Buzz Aldrin landed in a system that was never tested on the moon, which is in the current day and age completely unacceptable. And but if all that, we've mitigated all the risks, if then it still occurs, because there's always a risk, it's not a Boeing, and even a Boeing still has risks. If it then still occurs, that is the risk that the investor needs to estimate and take into his calculation when he signs the check. There's the risk that if it will happen or not, and there's the risk if we will recover from it or not. In the perfect world, I would like to have 2 missions going to Mars at the same time, 2 human crews going to Mars at the same time, such that the chance of failure is significantly reduced, because there is always, if we assume that we can only do a mission if the chance of 2 failures is almost negligible, then that would be the perfect world. But of course, it's very unlikely that we will be in that perfect world.
Rebuttal from MIT.
So I guess my question would be, you said you lay out all the risks very transparently and very transparently examine how you would mitigate them. One question that I have that I'd like you to lay out for us is, so say you launch the first cargo mission. So you've done the demo lander, you've done the rover that goes around and does all the stuff, and then you do the cargo mission that is tasked with producing the ISRU resources for the next crew. If it fails to produce those resources, or fails to get to Mars, or fails to land, or any of those things, then a lot of the value proposition of Mars One seems to be related to the human aspect, right? Getting humans onto the planet. If your first unmanned mission fails, the value proposition has not occurred yet, what do you do?
Well, that's a immensely crucial bit of technology, the ISRU. So it's actually already planned to be tested on our first unmanned mission, so the demonstration mission, the water extraction from the surface. I don't think that anyone is worried that we cannot extract nitrogen or argon from the atmosphere, but we can test that with relatively high fidelity here on Earth, and that's not the case with the surface. We don't know exactly what the surface will be like in the location where we land with the first unmanned mission. Then the rover will also have capabilities of, we don't know exactly to what extent yet. It will depend on how successful the first unmanned mission is, but it will also have certain capabilities of investigating the soil for suitability of extracting the water from it.
Okay, so it's getting towards 10 o'clock. So what I'd like to do now is have each of the teams wind up with a 2-minute concluding statement. MIT first? Just give a summary.
So I guess the key point that I'd like to bring this back to is the initial question of tonight. Is the Mars One mission plan feasible? We've presented the evidence that to us shows that it is not. I've heard an excellent case from the other side for why humans should go to Mars. I've heard an excellent case for why things are possible, but that's not the question. The question is this feasible? And I think that when we've laid it out here, the discussion has seemed to shy away from making the claim that the Mars One mission plan, which has been presented as a concrete object, 4 people to Mars in 12 years, $6 billion, building a crew over time, the launch plan that's laid out on their website, we have presented the evidence that we believe shows that it is infeasible, and haven't heard a response other than things may be possible and we should do these things. We totally agree that humans should go to Mars, but that's not the question of tonight. The question is the Mars One mission plan feasible? So that's really the point that I'd like to make is the Mars One mission plan feasible? And if it is not, what needs to change to make it feasible? We've discussed a lot of technologies. Those incur additional costs. Those incur additional time to develop. These are really the things that I think we leave it with, is this question, we've presented our evidence and have seen no evidence from the other side.
Yep, completely agree.
Mars One's plan is not to do the mission exactly in the way as it is described today on our website. Our mission is to have humans land on Mars, and to have additional crews go every 2 years. We have a early stage but executable plan for doing that. No new inventions are needed to send humans to Mars, to keep them alive there. We can do that. Our cost estimates have been discussed with very established aerospace companies that have been doing this for decades for the International Space Station, to the Moon, for Mars missions. We are confident that we can execute a plan that is close in the goals that it achieves, in the timeline that we present, and in the funding that we need for it. And we're very convinced of that because of all the good discussions that we've had with those aerospace companies. Thanks.
Thank you. Let's have a round of applause for both teams. That concludes the evening event. See you tomorrow morning at 9.